you to another statistical topic. Of course, before now, I actually walk you through some discrete probability distributions. We actually need uh, the probability distributions if we really want to understand events in a stochastic environment. Okay, and of course, you know, uh, I've walked you through a discrete probability distribution like Bernoulli, binomial, geometric, negative binomial, and so on, like that. And of course, with this distribution, we derive some basic statistics. When I say basic statistics, we derive the mean and variance. And what we're going to do today is actually the approach that we have been using all this while to derive the mean and variance, which we call moment. Okay, I'm going to walk you through moment, and I'm also going to walk you through an alternative approach that can be used to derive the mean and variance, which I also call the moment generating functions. Okay, I'm going to walk you through all of that. And let me also say this. It is not only mean and variance that we are interested in data. Okay, we're also going to look beyond that. We're going to talk about understanding the shape of the distribution, like talking about skewness and talking about kurtosis. Has anybody heard about skewness and kurtosis before in this class? Okay, so you're going to understand the essence, the meaning of skewness, the meaning of kurtosis, and how we're actually going to derive that from a given probability distribution. Okay, so I'm going to start with we got two material that are uploaded, and of course, starting with this. Okay, so if you take a look at definition one. If you take a look at definition one, if I have a random variable x, okay, a random variable s can be discrete or continuous. Of course, we've been working with a continuous random variable. Okay, if this random variable s actually is raised to a power, let's say r, okay, now if x is a random variable, even if it is raised to a power, that power is a constant, okay, it's still gonna the whole thing is still gonna be a random variable. That we can also think about. Well, of course, that is what we're doing in stochastic world, trying to find the average. Okay, now expected value of this. So this is the same as this. Okay, statistically speaking, this can also be written as this, and the name is root moment. We also call it root raw moment. Root raw moment. Okay, we also call it moment about zero. We can also call that moment root moment about the origin. Okay, please, I need you to pay attention to this particular formula. Okay, expectation of a random variable raised to power r. Okay, of course, this is the same thing as this. We actually call this arrow to rot moment, or we call it arrow moment about zero. Okay, it's like then we also call it arrow moment about the origin. Okay, now I'm interested in r equal to 1, 2, 3, 4. Okay. Now, if R equal to 1, if R equal to 1, I'm actually going to have this guy, which is going to be this, okay, which this is actually called first moment, okay, about 0. First moment about 0 is actually the mean, the expectation of S. Now, if I want to take S, if S is a discrete random variable, okay, if S is a discrete random variable, it's actually going to be this. Okay, depending on the state space. Okay, maybe the state space, of course, the state space is going to actually go from that to that, depending on the state space. And of course, the probability, this, we can also rewrite that as just simply that. If you write that as just simply that, okay, so I can also write this to be summation x f of s. Okay, now whenever this is the same thing as the mean, the first moment. Okay, we call it first raw moment, or you call it first moment about 0, or you call it first moment about the origin. This is that. Okay, now if I equal to 2 now, okay, if I equal to 2, okay, I'm actually going to have this, okay, which is going to be this. Okay, now what do we call this guy? This is second moment, okay, second moment, okay, about 0. Okay, you remember we've been working on this expected value of S squared. Okay, so if if S is a discrete random variable, if S is a discrete random variable, okay, this guy is actually going to be this f of s. Okay, don't forget I said f of s is the same thing as that guy could be whatever probability distribution. Let me just say s star from A to B, depending on the state space. Okay, let me be using A to B, depending on the state space of the particular distribution under investigation. Now, I can decide to go all the way. Okay, expected value of this now. Okay, so if I have this guy now, of course, let me just say this is I'm actually having, this is stop movement, is this expected value of that, and which is going to be that. Okay, and I'm actually going to go all the way. Okay, if R equal to 4, okay, I'm actually going to have this guy, okay, for discrete random variable, okay, for discrete random variable, I'm actually going to have that. Now, what I'm trying to say here, okay, you can see the first moment about 0, the second moment about 0. This is going to be the third moment about 0, and this is going to be fourth moment. Okay, now we normally stop at fourth moment, and you're going to see the reason why we stop at fourth moment. We don't go beyond fourth moment because the measures that we have in statistics, of course, we're actually going to use the combination of up to fourth moment. Okay, is there any question before moving forward?